Lab 2. Motion of a falling object. In this lab, I dropped an object from rest and then analyzed that video to understand the relationship between drag force and weight force and how it applies to Newton's second law of motion. Also, I was checking to see if the object had reached terminal velocity. In the tracker file, I analyzed the motion of an empty chocolate box dropping from rest. I held it against a column to make it easy to track the motion of the object, and chose the negative y-axis to be the direction of the object's motion. Here the graph of the object's motion in the negative y direction creates a curved graph, which implies that there was not a constant velocity. From Newton's second law, we know that a changing velocity means a non-zero net force. After gathering the data from Tracker, I constructed two models, one that accounted for the drag force and one that did not. In both models, the initial position wasn't at the origin, so I changed that and made the initial velocity 0 because the object was dropped from rest. Then the weight force was integrated into both models. G is the gravitational force and is set to 9.8 meters per second squared. J hat is the vector that allows for the calculation of the gravitational force because gravity is a force in the y-axis. In the loop, I calculated the weight force and assumed that it was the only weight acting upon the object, and then went on to calculate the ball's velocity and position using Newton's second law. Here is the model for the object with only gravity acting upon it. From graphing the model and the observations, it is easy to see that the model overpredicts the position of the object. So from analyzing this graph, we know that there must have been another force acting upon the object as it fell. This new force is the drag force. In a new code, I added in the drag force using the knowledge that the drag force is proportional to a proportionality constant times the velocity squared. The negative sign in the equation accounts for the fact that the drag force is in the opposite direction as the weight force. The proportionality constant was a value that we had to calculate using a trial and error method. In order to create the model to fit the observations, we had to force the model to match the final position of the observations. Using this trial and error method, I found a proportionality constant that made the model have a final position as the final position observed from the tracker file. As you can see, each time the code was run, a new final position was given. Here is the model with the drag force. The blue arrow represents the drag force and the yellow arrow represents the weight force. Then both models and the observations were plotted on the same graph. From this, we can see that without the drag force, the model overpredicts the motion of the object, but with the drag force, the model predicts the motion of the object properly. The object does not reach terminal velocity because it does not have a constant slope between any two time intervals. Also, the final drag force arrow is not the same size as the final weight force arrow. Thus, we can conclude that the object did not reach terminal velocity. If, instead, the object was dropped with an initial velocity, the object would eventually reach terminal velocity if the time interval were large enough. For this model, the time is 0.534 seconds. In that time interval, the object would not reach terminal velocity with an initial non-zero velocity. If the time was large enough, then the object would eventually reach terminal velocity before it stops moving. Once the drag force is larger than the weight force, the object will stop moving.